Hello, everyone. This is Giacomo Piccari speaking, and as usual, I welcome you to the new event of the Hypatia Colloquium series, which is, I remind you, this is a series which is dedicated to early career scientists, and is owned. As a matter of fact, all the speakers are early careers scientists, which means that either they are PhD students or obtained this PhD not more than 3 years ago. No longer than 3 years ago. So congratulations to everyone who has been selected, because the selection process has been very challenging. And so I always remind that this is really a pleasure for us to be able to host you in this platform and to give you this opportunity and of course to hear about your science. And very briefly, technically speaking, we are hosting the talks on the platform and streaming at the same time on YouTube. So participants should be aware that the series is streamed on YouTube live. If you are not comfortable with that, you can leave the event and still follow the event on YouTube, where you can also use the chat to send questions. Or at the same time, at the end of each talk, the chair will allow you to make questions by using you can raise your hand inside the Zoom meeting, and then basically you will be given the voice to make your questions or comments. The talks are 30 minutes, so each speaker has 30-minute slot, and we have, of course, as usual, two chairs chairing our session. Today we have Melanie and Paula. Melanie and Paula are two fellows here at ESO, and I would like to thank for their help, and it's very much appreciated. Thank you very much for helping us and for making the event possible. As a matter of fact, with this, I think I can immediately give the word to Melanie so you can introduce the first speaker. And Paula, thank you very much again, and see you later.
Thanks. So yeah, it's my pleasure to introduce today's first speaker, Piyush Sharda. So Piyush is a final year PhD student at the Australian National University in Canberra. There he studies the impact of metals on galaxy evolution. And as of October, he'll actually be in Leiden working as an audit fellow. So he'll go a little bit closer to us here in ESO. So I'll stop sharing, and then Piyush will tell us about the gas phase metal distribution in galaxies. Okay, you can go ahead and share.
Thanks, Melanie. Let me just share my screen. Right. Hi, everybody. Thank you very much for joining. So my name is Piyush, and I am just finishing my PhD here at the ANU, as Melanie said, and I'll be starting as a postdoc in Leiden in a couple months from now. So I thought today I'll share some of the work that we have been doing here at the ANU on understanding the distribution of metals in galaxies and how can we use metals to trace galaxy evolution, because these are nature's best tracers that we have available. And this work has been done in collaboration with quite a few people listed on the left-hand side of the slide here. So the reason why we can use metals to trace galaxies and galaxy evolution in general is very nicely highlighted in this particular movie from the Illustrious TNG project, where the different panels will show you the different properties, thermodynamic properties, as well as physical properties of the gas and stars and dark matter that we care about for galaxies. And we'll see that whatever processes and variations and dynamics that occur in all of these panels, for example, the gas temperature here or the gas pressure here, are very well mirrored in the effects on the metallicity in the gas phase in galaxies. So this is one particular illustrious galaxy, and the movie starts at redshift 4 and will go down to redshift 0. It's massive elliptical by the time it reaches redshift 0. And you can see, as you have accretion going on, the disk starts to form, and there's a rigorous star formation. And then we have these huge outflows because of starburst activity in the galaxy. And you can see that the signatures of all of these physical properties in different panels is very easily directly mirrored in the signatures of metallicity. So if we were to trace, if this was a real galaxy and we could trace its metal content over time and the distribution of metals in and around this galaxy over time, we'd be able to create a very good picture of how this galaxy has evolved. And this is the primary motivation for using metals as tracers to study galaxies. Now, global metallicities, or the overall integrated metal content of galaxies, has been very, very well studied. And we now know that there exists a fundamental relation between the metallicity in galaxies as a function of their stellar mass. Just taking this plot from Mirko Kurdi's 2020 work, where they plot the oxygen abundances, the total oxygen content of galaxies on the left and on the y-axis in absolute scale as a function of the galaxy's stellar mass on the x-axis. And we can see that even though there is a bit of a discrepancy in different results and different models and calibrations, the general result still exists, which is low mass galaxies have lower amount of metals. And the driver of this mass metallicity relation and the causes behind it are extensively being investigated, in particular in the last 20 years or so. And there's been a lot of research that has been done to interpret this shape and what causes this shape to come forth, and how does this shape evolve as a function of redshift. And in fact, in the last few years, we have also started to look and discover this MZR at higher and higher redshifts, going all the way to redshift 6 in some cases. So we know that this MZR exists and it evolves. However, this MZR really only tells us about the global content of metallicity. So there is more to be done in this area, and that's where integral field unit spectroscopy, or IFU spectroscopy, has changed the game, because using IFUs, instead of getting an integrated value or abundance of a particular element, we can obtain spectra of individual regions in the galaxy and thereby create a spatially resolved distribution of metals, or a spatially resolved metal map for different galaxies. So instead of having one particular fiber back from the SDSS days where you get integrated light together, we have a bunch of different fibers that we can place on different parts of the galaxy. And each of these little fibers here on the right give us a spectra from that particular part of the galaxy. And using IFU spectroscopy, we have now been able to measure spatially resolved metallicities and metallicity gradients in thousands of local galaxies. Here is a classic example, NGC 2997. It's a local spiral galaxy around 3 megaparsecs away. And we can see, so this particular map on the left-hand side is the gas phase metallicity, again, measured in 12 plus log over H units. The different little clouds that you see on the map are individual H2 regions that we can resolve. And then the spectra and the emission lines in the spectra then tell us something about the metallicity of that particular region. We can see that the metals here nicely trace the spiral arms in the galaxy. And if we were to deproject the different metallicities of these H2 regions as a function of radial distance, which is the middle panel here, we get a very characteristic profile, a metallicity profile, where we see that inner parts of the galaxy are very metal rich as compared to the outskirts. And this is what we would expect based on inside out galaxy evolution, that the inner parts of the galaxy form first. So they have had more time to enrich the gas around them and become more metal enriched. And subsequently, as the disk evolves over time, we have star formation occurring in outer and outer parts of the disk, which then also levels up their metallicities. One classic quantity that we have now started to investigate in these observations is the slope of this particular profile that we find. A simple 1D fit to the profile, and the slope is what we call is the metallicity gradient. It's measured in a few different units that you will see throughout the talk. Physical units being dex over kpc or dex over RE, where RE is the half-light radius of the galaxy in question. So studying these metallicity gradients has become the prime focus when we talk about spatially resolved metal distributions in galaxies, because we have now been able to measure these metallicity gradients for a lot of galaxies, both in the local as well as the higher redshift universe. And only in the last few years have cosmological simulations like the TNG again have started to produce these metallicity maps in their galaxies and then compare with observations. But we still lack a physical model that talks about metallicity gradients and not only about global metallicities in galaxies. So to model these gradients, we really need to understand the life cycle of metals in galaxies. Metals follow a very simple life cycle in galaxies, and this is nicely summarized in Simon Lee's 2013 work, which is very well known as the bathtub model of chemical evolution now, where we have the galaxy disk is represented by this bathtub here, which is residing inside a dark matter halo. Gas enters this halo through accretion from the cosmic web. Some of this gas inflows into the galaxy. It will ultimately become the fuel for star formation and trigger star formation, which will then produce metals. Some of these metals will be locked in stars that live for a long time, so low mass stars. But a lot of the metals are instantaneously returned to the ISM of the galaxy through supernovae or Wolf-Rayet or stellar winds and so on. And throughout this process, we also have a loss of metals in the form of galactic winds and outflows. So it's a very dynamic life cycle. All of these things are more or less happening simultaneously in the galaxies that we see today. But they can be classified in a few different, the life cycle itself can be classified in a few different stages, where we have production of metals due to star formation, as well as in the interiors of stars and mergers with neutron stars and black holes and so on. We then have consumption of metals due to star formation and stellar atmospheres and so on. Metals are also moving around the galaxy because they are being advected by the gas. So they move with the bulk motion of the gas. They also diffuse in galaxies, and then they're accreted from the CGM or the IGM. And while all of these processes go on, metals are also lost through winds and outflows and so on. However, this particular model was designed to explain global metallicities and the MZR. So it still lacks some features that are important to understand the spatially resolved metal distribution of galaxies. So for example, existing models do not really include all modes of metal transport. The ones that I mentioned in the last slide, advection, diffusion, and so on. Several of these models that we have assume that the metallicity of the outflow is the same as the ISM metallicity. And we have started to see observational evidence that is not the case. So we do see in a lot of galaxies where we can measure the wind metallicities, that the winds are more metal enriched as compared to the ISM. And we'll see later in this talk that this is an important assumption that you once drop opens up a lot of answers, but as well as questions about how metals are tracing galaxy evolution. And finally, the model parameters are not independently constrained by ISM or galaxy theory. This is where we come in, where we have developed a new comprehensive model to explain the physics of metallicity gradients in galaxies, where we include things like radial gas flows through the disk. So that is essentially advection of metals. And we also include diffusion of metals in the disk. So metals diffuse because metals will diffuse from a high concentration area to a low concentration area. And thereby the distribution of metals will become more homogeneous. It turns out that once we do these sort of improvements, we also do not assume that the wind metallicities are the same as the ISM metallicities. We can then apply the same model to a wide range of galaxies, both in the local and the high redshift universe. And the model parameters that we obtain for this model are independently constrained by galaxy evolution theory, which simply means that metals are being self-consistently treated with stars and gas in the disk of the galaxy. I'll discuss a couple of, in the rest of the time that I have, I'll discuss a couple of applications of this model, and we'll see how using these models and comparing them with data can tell us a lot of things about the evolution of galaxies as a whole. The first one of these is the local mass metallicity gradient relation. So like the MZR, this is the scaling of metallicity gradients with galaxy mass. This is still a relatively recent finding because the MZGR has only been produced very recently, since 2014 or 15, from a few different IFU galaxy surveys. And the origin of the MZGR is still not well understood. It's a matter of debate as to what causes it and what are the drivers behind it and so far. So what I'll do is I'll first show you the results from the model, and then I'll overplot the data that we have currently on top. So this is how the mass metallicity gradient relation from the model looks like. So the x-axis here is simply the stellar mass of the galaxy. The y-axis is the metallicity gradient measured in dex over half-light radius. And the color bar here is the ratio of two different physical processes that can dilute or homogenize the metal distribution in galaxies. So if these processes are really, really strong, the metal distribution will be homogeneous. So the gradient will be 0 because it will not have a metallicity profile that changes with radius. So these two quantities are radial flows through the galaxy, through the disk, and gas accretion. So if we are on the blue side of this predicted curve space of the model, it means that gas accretion dominates, and that's the dominant process that will decide what sort of metallicity gradients should galaxies have. And accretion is the one that will compete with star formation in galaxies to give rise to flatter gradients. If we are on the very red side of the curve, that's where advection dominates, because accretion becomes weak for lower mass galaxies, and radial flows or advection then competes with star formation to decide the strength or of the gradient or the steepness of the metallicity profile. And there is a transition regime between the two where both of these processes are weak. So galaxies might be able to drive stronger, steeper metallicity gradients. You'll also notice that the model has a vertical spread. So for each particular stellar mass, we are predicting a range of metallicity gradients. And this spread comes from uncertainties in the metallicities of galactic winds. So we have really no constraints on wind metallicities so far, because wind metallicities have been measured for only a handful of local galaxies, less than 10 as far as I'm aware. So we have to leave this as a free parameter in the model. But what this basically means is if galaxies tend to preferably lie on the upper edge of the predicted space, it means that the wind metallicities are very high as compared to the ISM metallicities, which means galaxies are preferentially losing more metals in their winds as compared to the ISM. However, if galaxies prefer to lie on the bottom of the predicted space, that just means that the wind metallicities are similar as the ISM metallicities. So metals are very well mixed into the ISM before they are ejected in the form of a wind. And this is how the data looks like. So the data comes from 3 different surveys, Manga, Khalifa, and Sami, which are represented in the orange markers here. And the gray marker is the overall mean of all of these different surveys. And there are quite a number of interesting things we can learn from this comparison. I'll only highlight the 2 key points that we can take away. Firstly, we do see that galaxies transition from a radial inflow dominated regime to an accretion dominated regime as the stellar mass increases. And this sort of a transition from inflow dominated to accretion dominated regime, that mirrors the transition that people have seen in the drivers for gas turbulence in galaxies. Secondly, we see that all the low mass galaxies preferably lie on the upper edge of the predicted space of metallicity gradients in galaxies. So this comparison immediately tells us that low mass galaxies preferably lose more metals in galactic winds. And this is a somewhat stronger prediction of the model. Again, we only have a very low number of observations to test this thoroughly, but this is where I think we are heading towards. We are heading towards an regime where we can really measure wind metallicities and the metal content of the CGM, because this sort of a comparison also has important implications for the evolution of the CGM. In the rest of the time, I'll now show you another application of the model that we have, where we apply the model to high redshift galaxies, and we study the trends between gas kinematics and metallicity gradients. And the reason for that is very simple. We do expect that in addition to galaxy mass, the kinematics of the gas, and by that I mean the velocity dispersion of the gas or the rotational velocity, will also have an important role to play in setting the metal distribution in galaxies. The reason we go to high redshift for such a study is because in the local universe, we really do not have a bigger dynamic range of gas kinematics to play with. And this is nicely summarized in this plot that discusses the evolution of ionized gas velocity dispersion as a function of redshift. It's a very popular work from Wisniewski et al. 2015, where we see that at redshift 0, the gas dispersion is usually between 10 to 20 kilometers per second in almost all galaxies. But as you go to higher and higher redshifts, it evolves over time such that between redshift 0 and 2, we have a much larger dynamic range of gas velocity dispersions. And we can then use this to test whether we can say something about how gas kinematics impact metallicity gradients. This is an area where we are expecting a lot of data to soon come in from instruments on the VLT, like MAVIS and MOONS, as well as JWST. This is how the model predictions look like. But instead of showing you the entire vertical spread in the model, I am only showing the steepest metallicity gradients the model can produce for a given gas kinematics. So the x-axis here is the gas velocity dispersion. The y-axis is the metallicity gradient. And the different colored curves represent the steepest possible metallicity gradient for different values of the rotational velocities, so which is sort of a proxy for stellar mass. We see the same transitions as we saw before, where accretion tends to dominate at lower gas velocity dispersions. Radial flows tend to dominate at higher gas velocity dispersions. And wherever these two are weak, which is at intermediate gas velocity dispersions, that's where we expect the steepest possible gradients to be. So this is sort of a bound that the model is predicting we should see in the data. We should not see a lot of data which should lie beyond these lines for the given stellar masses and rotational velocities. We have very few galaxies, again, at high redshift where we can measure the metallicity gradients. And the sample itself can be a bit inhomogeneous. So what we have done is we have taken data from the literature and tried to reanalyze the gas kinematics in a very consistent manner so that we can then put all of that data together and compare apples to apples on the same map. But as you can see, there's still big uncertainties, and we only have around 70 galaxies at the moment for which we could do this sort of a comparison. So this is, again, looking forward more to the future rather than having strong conclusions today. And this comparison between the data and the models, where we're not really fitting any models to the data, we're just simply overplotting them, again, tells us some interesting features about galaxies. So we see that in galaxies with very, very high velocity dispersions, we expect very flat metallicity gradients because we expect metals to mix efficiently throughout the disk. At very low velocity dispersions, we see efficient dilution of metals. So the overall metal content of the galaxy is lowered such that we again see flatter gradients. And it is at intermediate velocity dispersions where we see a larger range, a big scatter in metallicity gradients. This is probably highlighted better in the second plot, where the x-axis is the same, it's the gas velocity dispersion, but the y-axis is the scatter in the model and the data. So what matters here for this sort of a comparison is not the absolute values of the scatter function, but the shape that they have. And the shape of the scatter function that we see in the data is well reproduced by the model, and which just immediately tells us that one of the reasons why the scatter in the data is the way it is could be due to, again, the metal enrichment of winds. But that is only one of the possibilities. We can, of course, have other things going on at high redshift as well. And this is an area that we are very eager to explore more with upcoming data from other facilities. So I can summarize there, where we have, I have presented our model for gas phase metallicity gradients, which talks about the physics of metal distribution in galaxies. And the key improvements that we have is that this model includes all major modes of galactic metal transport, as well as differential enrichment of galactic winds. And because it is constrained by an independent model for galaxy theory, an independent model for gas in galaxies, there are no free parameters in the model except for the wind metallicity. We have seen that to explain the local mass metallicity gradient relation, we require that galaxies transition from an advection dominated regime to an accretion dominated regime as they increase in mass. We have seen that low mass galaxies preferentially lose metals in winds, and this is a prediction that needs to be confirmed further through observations. For massive galaxies, we always see flat metallicity gradients regardless of the nature of their winds. So it simply means that in massive galaxies, winds are not really impacting the metal distribution of the disk itself. And again, we have seen that gas kinematics definitely play a big role in setting metallicity gradients. And there are some important predictions the model has, which will be tested in the near future. The details are in a set of papers that we have, and I'll be very happy to take any questions now or correspond later over email. Thank you very much for your attention.
Thanks a lot, Piyush. That was a really lovely, clear talk. I'm just going to wait a moment because usually the questions take a moment to come in. So also, Giacomo, if there's any questions from the YouTube chat, I might just take the opportunity to ask the first question. Yeah. So you showed the bathtub model at the beginning, and one of the main assumptions of that is that the metallicity of the wind is the same as of the ISM.
Yeah.
Now, with your more all-encompassing physical model, can you test how accurate that assumption is? So is it systematically over or under predicting the metallicity of the wind?
Yes. So what we are finding is that if we make this assumption that the wind metallicities are the same as the ISM metallicities, then we are systematically under predicting the wind metallicities, especially in low mass galaxies. So there's a recent work by John Chisholm where they measure the wind metallicities of 6 galaxies, but 3 out of those 6 galaxies are low mass galaxies, so lower than the mass of the LMC, for example. And in all of these galaxies, they find that the wind metallicities are as high as twice or thrice the local ISM metallicity. So this is definitely an assumption that we need to drop, in particular when we talk about metals like oxygen, which are produced in type 2 supernovae. So even simulations of low mass galaxies are telling us that a lot of metals are preferentially ejected. So this assumption definitely needs to be dropped if we want to look at low mass galaxies in particular. Yeah.
So then this has implications more for the MZR relation at low stellar masses rather than at high stellar masses, right, which is usually compared to observations.
Right, yeah. Okay. So it has more implications for the MZR and the MZGR at low mass, and that's
great. Thank you. Hopefully it's just at my end that Piyush is breaking up. I can't see any questions.
Sorry.
Melanie, I think Simon has a hands raised.
Okay. Yeah, go ahead, Simon.
Hi, thanks. Thank you for the talk. I guess this might be outside the scope of your model, but I was wondering whether you would expect this metallicity gradient to continue into the CGM, so beyond the ISM.
Piyush, sorry, we have a quality.
Yeah.
there is a I don't know. Melanie, do you have the same issue?
I'm sorry.
Yeah, I have the same issue. Maybe we should have some of the questions at the end, because it seems like it's at Piyush's side.
Maybe you can, exactly, or you can, okay. Yes.
Yeah.
It's gone, I think. Okay, yeah, maybe.
I'm happy to put it into the chat as well.
Okay, great, yes.
For later. Yeah.
Thanks.
Okay, so should we try it or pass on to the next speaker?
Oh, let's try again. Simon,
okay.
Simon, you want to try?
Piyush, you look like you're live again now for me.
Yeah, hi, sorry about that. Yeah, it's probably a sort of an unstable connection, but I can hear you guys now. Thank you.
Very good, no problem.
Okay, perfect. Yeah, so my question was, this I guess might be outside of the scope of the models you were working on, but would you expect this metallicity gradient to extend into the CGM, or would the behavior be, I guess, different?
Right, yeah, that's a very good question. We really cannot answer that based on these models, but simulations, not really cosmological simulations, because the resolution to do that in the CGM is still not good enough. But isolated galaxy simulations have definitely started to see some sort of a metal distribution or a gradient in the CGM. Doing this in observations, I think, is still very tricky, but that is somewhere where the galaxy evolution community as a whole is trying to reach, to really map the metal content of the CGM. I think one of the biggest challenges we have there is we have a lot of multi-phase gas, and it becomes really hard to, for example, if you're only looking at the ionized phase, you might not be seeing the overall metal content because you're ignoring the X-rays and vice versa. So that's the next frontier that we are looking at and trying to use that to constrain our galaxy evolution models better. But there's a good chance we might see some sort of a gradient in the metallicity in the CGM. Yeah.
Thank you very much.
So we have one more question from the YouTube chat, and we'll try to make it brief. So this question is from Celine Peru. You made the point that IFUs now provide resolved maps which capture the metallicity variation on small scales. These features are not captured by metallicity gradients. What are the prospects of quantifying metallicity structure in both observations and in models?
Right, yeah, so a lot of people have started working on this already. So going beyond the metallicity gradients picture, because when we talk about metallicity gradients, it's sort of a first order approximation to the to a realistic metallicity map or a profile that we have from galaxies. So now, instead of throwing away the 2D information, people are now trying to quantify things like metallicity asymmetries or metallicity correlations, which use the entire 2D information that we can get from these sort of IFU surveys. And doing this in models, this has been done. So on a statistical level, there are models that exist which talk about the 2D correlation of metals and use that to quantify metal content in galaxies instead of metallicity gradients. But there's only one such model that I'm aware of. This is still a very new field. And again, we do not have data for thousands of galaxies for which we have done this so far. This has only been tried on a very handful of galaxies using Muse observations. This is again something we are considering, or we should definitely consider in the near future.
Okay, thanks a lot. I think that was it.
Thank you.
From the questions, I don't see any more hands up, so I think we can pass on to the next speaker. Thanks a lot, Piyush.
Thank you.
Okay, so hi everyone, I'm Paula Sanchez, and I have the pleasure to introduce Luca Ighina, who is a PhD student at Università degli Studi dell'Insubria and in Milano Brera in Italy. And he will talk about impact of the CMB on the evolution of AGNs and their relativistic jets at high redshifts. So you can share the screen now.
Okay, perfect. Thank you, Paula. Let me share the screen.
Okay.
Here it is. Okay.
Yes, we can see the specs.
Okay, can you hear me well too?
Yes.
Perfect. Okay, so, well, first of all, thank you very much for giving me this opportunity. Really appreciate it. And today I would try to talk about what I've been working on during the first half of my PhD. In particular, with the collaboration of the people that you can see at the bottom of the screen. And so the focus of this talk is going to be the impact that the cosmic microwave background might have on the jets of AGNs at high redshift. So this is more or less the outline of my talk, where I'll start with a brief introduction on the specific class of blazars, and then also on the properties of large-scale relativistic jets. Then I'm going to focus on the specific study that we did on this particular source, a redshift 6.1, and then I'll try to generalize our this sort of studies to the overall blazar population, focusing on their space density evolution. And finally, I will try to summarize very briefly our current efforts to expand this type of studies even to higher redshift, and also to how we can put them on a more solid statistical basis. Okay, so well, let's start talking about active galactic nuclei. So AGNs are extremely bright galaxies where the supermassive black hole in the center is undergoing an accretion process. Now, a fraction which is about 10 to 15% of them, which is normally referred to as radio-loud AGNs, is even able to expel part of the accreting matter in the form of two very powerful relativistic jets. And one of these two jets is oriented very close to our line of sight. We call this source a blazar. Now, the particular orientation of these sources makes them extremely bright, because the radiation produced within the jets is relativistically boosted. And this also makes blazars the ideal laboratory where to study the properties of relativistic jets. Indeed, as you can see in this plot, which reports the spectral energy distribution of a typical blazar, you can see that the radiation produced within the innermost regions of these jets, well, first of all, spans a huge range of frequencies, and also that it dominates the overall output emission of the AGN, both a low frequency, a very low energies, and high energies. In particular, the main mechanism responsible for the radiation observed at low frequencies in the radio band is the synchrotron process, where the electrons interact with the magnetic field lines. Whereas at high energies, the main mechanism responsible for the emission observed in the X-rays and in the gamma rays is the inverse Compton scattering of these electrons with seed photons, where these seed photons could either be the photons produced through the synchrotron emission by the same population of electrons, or they also could come from they could also be external photons, meaning that could be produced by other AGN components. And in particular, at this very high energy emission, is produced mainly in the innermost regions of the jet. And so I'm talking about parsec scales, even less. And so when we look at blazars either in the X-rays or in the gamma ray band, we should see them as very, very compact objects. However, here I show you an example of this source, PKS or something, in the X-ray, in the radio, and in the optical. And as you can see, the image, which was obtained as the first ever Chandra observation, was able to, with this telescope was able to resolve and detect a very quite bright emission from the very large scale jet. And by large scale, I mean many kiloparsecs away from the central engine. And after this discovery, the community was very surprised, because while at the lower frequencies, we can still explain this emission at large scales with the synchrotron emission, with the synchrotron process. At high energies, the origin of this radiation is not that clear. This is, first of all, because at these very large scales, there are no other AGN components that could provide seed photons that can be then upscattered to the X-rays. and also because the intensity of this emission is orders of magnitude larger, higher than what one would expect from the inverse Compton scattering of the photons produced through the synchrotron. So one of the first and most popular interpretations of this emission was that this radiation is produced again through an inverse Compton interaction of the electrons within the jet, but this time with the cosmic microwave background photons. Because this photon, the cosmic microwave background, fills all the universe. It's everywhere in every single region, so it's also going to interact with the electrons within the jet. And in particular, if we take a look at if we consider the typical energies of the electrons within the jet, we can see that the radiation produced through this process is expected to be in the X-ray gamma ray band. However, one of the problems with this model, it was that it required quite extreme physical conditions of these jets. For example, it required that at these very, very large scales, the jets are still highly relativistic, and I'm talking about bulk Lorentz factor of the order of greater than 10. And also that pretty much all of these jets were seen at very, very low small viewing angles. But then things got even more complicated with the launch of the Fermi Gamma Ray Space Telescope. This is because, as I mentioned before, with the inverse Compton CMB process, we do not only expect the X-ray emission to observe X-ray emission, but also a very strong gamma ray emission. That, however, was not detected in many sources in the local, at low redshift. And so for these systems, these non-detections with the Fermi telescope implied that the inverse Compton CMB process is not the main contributor to the observed X-ray radiation. And at the same time, this also means that there must be another mechanism at place here that's producing the X-ray fluxes that we're observing. And the simplest solution to this is the presence of a second population of electrons, but which needs to be accelerated up to very, very high energies in order to then emit X-ray radiation through a synchrotron. Now, in any case, the inverse Compton CMB process cannot be completely abandoned because this is an unavoidable process. I mean, the jets are there, the electrons within the jets are there, and also the CMB photons are there. They're bound to interact, for sure. The only problem now is to understand what is their relative contribution to the observed emission with respect to this potential second population of electrons. And this is important to understand because different contribution might result in different physical conditions of the jet at these large scales. And so if we want to constrain the importance of this process, we have to keep in mind two things. The first is that the energy density of the CMB has a very strong redshift dependence. Indeed, going at higher redshift, it increases very fast. And this also means that inverse Compton CMB process is going to be much more important at high redshift. And the second thing is that there are a couple of sources in a low redshift where actually the gamma rays observation confirmed and were consistent with the expectation from the inverse Compton CMB model. And the common feature of these sources was that they are all blazars, and so they are seen at very small angles. And so, as you can see, the best way to try to constrain this type of process is to focus on the high redshift population of blazars. And this is where my work comes in. In particular, in this paper that you can see here, we performed a detailed study of this specific source, PSO J0309 plus 27, which is the highest redshift blazar currently known at redshift 6.1. Now, this source was discovered by Silvia Belladitta from our group a couple of years ago. And if we compare its radioluminosity to the other radio loud AGNs currently known at high redshift, you can see that this source is one of the radio brightest at these redshifts. Not only that, but also very high-resolution observations in the radio band showed the presence of quite beautiful relativistic jet that is extending up to several hundred parsecs away from the central engine. And so the combination of the very high redshift, the radio brightness, and the presence radio of extended jet at millisecond scales makes this source the ideal candidate where to look for and potentially study the emission of large scale jets. And so to this end, we performed a relatively deep Chandra observation. And indeed, thanks to this observation, we were able to confirm, to identify and discover the presence of a relativistic jet extending up to several kiloparsecs, and in the same direction as the jet observed at higher resolutions. And also, we also found this especially that this jet is special. I mean, there's a coincidence with the radio signal from the VLS survey. And so this discovery makes this jet the most distant, a large-scale jet currently known. And so potentially it could provide the most stringent constraints on the properties and the evolutions of these jets. And so what we did was to study its multi-wavelength emission. In particular, we modeled the spectral energy distribution of this source, which you can see reported here in red. And the first thing that we found was that its X-ray emission is fully consistent with the inverse Compton CMB model, even without requiring the very extreme parameters that are needed in the local universe. And this is mainly due to the fact that at this very high redshift, the cosmic microwave background energy density is so strong that it boosts this process by orders of magnitude compared to the local universe. But also, that's another interesting thing that we found was that during our modeling, we also considered the potential, the emission from a second population of electrons through synchrotron. However, what we found is that this type of emission in the X-rays is inefficient, and this is because, again, due to the very high energy density of the CMB, the cooling timescales of the electrons through the inverse Compton CMB process are so short that that electrons cannot even be accelerated up to the very high energies that are needed in order to for them to produce X-ray emission through synchrotron. And so the sort of the picture that comes to that we got from our study is that the high energy emission observed in the large scale jets is given by both the inverse Compton CMB and the synchrotron mechanism, while the synchrotron process will dominate in the lower redshift, the inverse Compton CMB will become more and more dominant at higher redshift. But not only because this mechanism is boosted by the increase of the energy density of the CMB, but also because the synchrotron emission is quenched going at higher redshift. Okay, so this was like a specific study on one single source. But now let's try to understand what we're expecting on the much broader population of lasers. And in particular, if what I've been saying so far was true, we would expect that the overall X-ray emission, and by that I mean the overall emission, so the one also not resolved by current instrumentation, we expect this emission of the luminosity, X-ray luminosity of lasers to increase with increasing redshift. And it is what we found actually. In particular, we compared the X-ray to radioluminosity ratios of a statistically complete sample of lasers at high redshift. You can see here reported with the orange histogram and on the right with the red points as a function of redshift. We compare these ratios to their low redshift counterparts, in both cases here reported in blue. And as you can see, these distributions are quite significant, significantly different, with high redshift lasers having on average 2 times X-ray to radioluminosity ratios 2 times larger than the low redshift. And now if we interpret this difference as due to the inverse Compton CMB process, we can write the energy, the evolution of these ratios as a function of redshift in this way, where there's a term which is not evolving with redshift, and then there's a term that does evolve with redshift following the evolution, the increase of the energy density of the CMB, and where the A0 parameter is the relative importance of this process at redshift 0, and which, based on the samples, the complete samples that I showed before, we found was quite almost 0 in the local universe. And understanding this evolution trend is important also because it could actually explain, it could solve one of the problems that is still open in the studies of lasers. And in particular, I'm referring to the fact that the space density evolution of lasers is significantly different when we look at them in the radio or in the X-ray band. As you can see here in this plot, where I reported the observed X-ray space density of lasers with these green points, and then also, and while the blue curve is the expected evolution of the space density of lasers computed from starting from radioluminosity functions and then assuming a constant X-ray to radio conversion factor. As you can see, these two are significantly different. First of all, in normalization, but also maybe also in at the redshift peak. And understanding this difference is, let's say, it's very important, especially if we want to use to understand it, to trace the evolution of supermassive black holes hosted in jetted systems up to the early universe, and so to their formation. And one possible solution to this problem, it could be that actually this converting factor is not constant in time. And so what we did, it was checking whether the expected trend of the inverse Compton CMB process can actually explain this discrepancy. And the answer that we found was yes, it actually can. And as you can see in this with this red curve that we computed now also included this this additional term related to the inverse Compton CMB interaction. And as you can see, this curve can reproduce quite well the observations. And however, one of the predictions of this model is also that at high redshift we're expecting to observe a lot of very X-ray powerful lasers. And so one way to test it or to further constrain it is to exploit the eROSITA mission, which is currently scanning the entire sky in the X-ray band. And in particular, based on the relative importance of the inverse Compton CMB process, we expect to observe a significantly different amount of lasers at high redshift. But not only that, but they also will have a different redshift distribution. And moreover, since eROSITA is an X-ray telescope, it will only select only the most powerful sources, which then can be studied singularly with the Chandra telescope, as I showed you before, to put further constraints on this process. However, as I mentioned, the eROSITA is going to only select the brightest X-ray end of the laser population. While if we wanted to have a look at if we want to have an unbiased look at the entire population of lasers or radio-loud AGNs at high redshift, we should start from the selection from another band, in particular from the radio. And this is what we're currently doing. based on using the Rapid ASCAP Continuum Survey, or RACS, which is the first radio survey performed with the ASCAP telescope, which is one of the SKA precursors. And in particular, using this survey, we are building the first complete sample of radio loud AGNs at redshifts above 5. And while the spectroscopic confirmation of our candidates is still ongoing with the major optical telescopes, I can show you that we already were able to identify 3 new radio loud AGNs at redshift above 6, where to date only other 4 are known. And we are currently right now gathering multi-wavelength information from the radio to the X-rays in order to constrain their properties, and also the properties of specifically the properties of their jets. And with that, I leave you my conclusion, and thank you very much for the attention.
Thanks, Luca, for this talk. Very interesting. For the moment, I don't see any questions here. Okay, so in the meantime, maybe I can ask. So the numbers you're using now, the number of sources is kind of low. So in order to have much better statistics, do you think future missions like LSST or Athena maybe will help to these kind of studies?
Yeah, specifically, I mean, as I mentioned, the Rosita would be extremely useful to select high redshift lasers in the X-ray band. For example, while the LSST, I mean, wait, what do you mean by?
Because you can,
like, for example, this sample.
Yeah, I'm thinking about like finding new high redshift lasers from LSST.
Yeah, I mean, you have to keep in mind anyways that lasers are extremely rare sources. Also,
yeah, I know.
But yeah, the LSST is going to be the game changer, because I mean the locking point in the funnel right now is the optical, because with radio surveys that we have, we can since lasers are the most radio brightest normally of the AGN population, with radio surveys we don't need to go that down below. I mean, EMU is going to be EMU or other ASCAP surveys is going to be very helpful. But the problem right now is with the optical surveys, because we have to identify them. We have to have an optical counterpart in order to identify the redshifts, and also and so yes, with LSST, actually I can show you also. I have some predictions. With the LSST, we expect to find also after the first year, we expect to find a lot of new blazers, and even many more radio loud AGNs in general.
Yeah, because it's just a suggestion from the point of view of variability, since blazers vary in a very rapid way.
Yeah,
you can use not only the brilliant fields but also the white fields from LSST to find them. Just a suggestion.
We've thought about it, but it depends, because in the optical, we are especially at high redshift, we are sensitive to the flat spectrum radio quasars population of blazers. And so where in these sources are where in the optical we're observing actually this component is where the jet emission is lower, the lowest. And so variability, in the optical they look like other AGNs actually.
Okay, and what about Athena? Because there is a huge effort now to keep Athena alive.
So, yeah, I know.
So maybe we can use this kind of science cases.
Athena will be since it won't perform very large area surveys, Athena will be, in my opinion, will be very useful to perform more detailed studies, such, I don't know, as the one that I showed you with Chandra. I mean, Chandra has a better resolution, but still with Athena, if we have a resolution of a few arc seconds, it would still be possible to sort of resolve this kind of jets. And with its collective areas, it's going to be very easy. We can do this for a lot of many sources. Yeah.
Great. So do we have questions from YouTube? I don't see any in the chat. Not here in the chat or in person. No, okay. So I think with this we can end this session. Thanks, Luca, for your talk.
Yeah, thank you very much, Paula. Sorry, thank you, Luca, and of course, Pia and Melanie and Paula, you're both for chairing the session. Congratulations again. And please be reminded that the talks will stay online. They are available on the YouTube chat, playing list, so you can go and watch them later. And also the CVs of our speakers are available online. You can go and download them from the program pages. And also our speaker will send us proceedings, a book of proceedings that we will publish hopefully during the summer. So you will be able also to see the contributions in a written form. Thank you very much again to everyone, and see you next time. Next week is going to be the last one, unfortunately, but then the summer comes. Thank you very much again. Ciao, everyone.
Bye.
See you.
Thank you.
Bye.
Bye.